So welcome to the seminar of the SONY Astani Department of Civil and Environmental Engineering. Today our speaker is Mohammad Ali Ghannad. Comes from, as his name indicates, Iran, and from Sharif University. He is actually presently a visiting professor at Stanford University. It's quite curious to learn about his courses. He got his PhD in Japan at University of Nagoya. Now that's not a usual courses, and congratulations for that. So we're going to hear today from his talk about soil structure interactions. So again, let's just welcome Professor Ghannad. Welcome.
Ladies and gentlemen, thank you, Professor, for introduction. I'm really happy to be here in University of Southern California to talk about our research topic, soil structure interaction in Sharif University of Technology in Iran. And I'm really honored to be with researchers and professors here in USC, which indeed some of them are pioneers in the field. Actually, before starting, it's my first visit to University of Southern California, but somehow I feel that I'm at home. First, because of the hospitality of the faculty members here that really made that I feel that I'm home. And also because of the many familiar faces. We have many graduates of Sharif University here, and really I'm happy for them that have the privilege to study in University of Southern California. The topic is the effect of soil structure interaction and seismic response of structures. It seems to be general, but actually, as I will explain, mostly I'm going to talk about the effect of soil structure interaction on inelastic behavior of structures, and using simplified models as simple as possible to look at the global response of the structures. First, let me have an outline for the presentation. First, start with introduction. Of course, as I said, many of you are very well familiar with the soil structure interaction, but usually the soil structure interaction is not so attractive subject for the whole engineering community, so the civil engineers. And I start with a very short introduction about the state of the problem and what is the soil structure interaction is. Then I go briefly to the current seismic provisions that include the soil structure interaction, and then go directly to the general effect of soil structure interaction and seismic behavior of structures, which include the effect on the elastic response of structures, inelastic response of structures, and as I said, I'm going to focus in this part especially. And when you have an inelastic behavior, of course, there would be energy absorption and damage. So we talk a bit about the hysteretic energy demand and the effect of soil structure interaction and the hysteretic energy demand, and also the damage index. This is done mainly for the surface foundations, but again, I a bit go to the extension of the results for the embedded foundations. Of course, for talking about the effect of soil structure interaction, we need a model, and we use a simplified model for the soil structure system. And finally, go to discuss about the current US provisions. When I say US provisions, I don't mean that specifically I want to talk about the US, not the other countries. It means that the state-of-the-art provisions, which is the American standards for the design of new buildings and also for the rehabilitation of existing buildings. Okay, the state of the problem, of course, during the earthquakes, source problem, we have a past problem, and also the local site The figure is from the Kramer with some modification in this part. Of course, I added some buildings here. And here today we are going to focus on this part, the effect of the local site, which can be partly the soil structure interaction effect and the site effect also. Then I will explain in the next slide. And the main purpose is that saying that the fixed base structures built on the rigid soil is not equivalent to the those built on the flexible soil. Of course, this is the real case that you have that, but the results which comes from the models of the structures on the rigid base, we have to think about the reliability of the results. I borrowed this figure from somewhere. It's not mine, but unfortunately I don't remember from where. Anyway, suppose that we have site is a rock, for example. Of course, the ground motions in any two points you cannot find with it completely identical, similar to each other. But suppose that we have similar ground motions in the point A and point B, considering that the distance here is comparatively shorter than the place that waves come from. But when you have soil, of course, you have waves propagate through the soil layer to the surface, and of course the motions on the site and the surface would be different from those recorded on point B. And this is the phenomenon that we usually name it as the site effect. Now, consider that we have two different sites, but by chance, we have the same ground motions. This is on the rock, and this is the soil. But by chance, just suppose that have this is after the site effect, and this is the original record on this rock. We have the same records, but the response of identical structures on these points would be different again. And this is due to the soil structure interaction because of the flexibility of the soil, and the flexibility of the soil changes the response even to the same excitation. And this is the point that we are going to focus in this part. Of course, that one is also known from early years of the earthquake engineering, the site effect, but we are mainly going to focus in this one. So this aside, the soil structure interaction changes the response. But looking more closely to the soil structure interaction effect, we can divide it to two main parts, the kinematic interaction and the inertial interaction. For the kinematic interaction, suppose that we have a free field, and suppose that this wave coming from free field, it means that there is no structure, no excavation. When you insert the relatively rigid foundation to the soil, suppose there is no mass, even no mass, the response of the motion of the foundation, of course, cannot be the same as the soil. So they have to compromise each other to move to some extent. And when you say, for example, see here, it moves to different parts, different ways. And for example, in this case, rotational motions can be resulted to the structure, to the foundation. But in this case, for example, you can see the same, but maybe they cancel each other. So it means that the relative dimension of the foundation to the wavelengths is a key parameter. So the high frequencies can be filtered by the relatively rigid foundation. So considering that, of course, the seismic waves is a combination of different frequencies. And finally, this is usually we use that for the cancellation of the higher modes, the relative dimension of the boat, for example, on wavelengths is, I borrowed this from my professor Fukuwa. He used to use this slide. And
do you know where he got it from?
Pardon?
Where did he get it?
Oh, I don't know exactly. Actually, when I wanted to prepare this slide, at that time I thought that he maybe also by himself borrowed this from somewhere else.
Let me tell you, the first director of the Earthquake Research Institute, his name was Soyehiro, was a naval engineer. And he came and lectured in this country in 1932, and he did quite a bit of discussion of exactly this type of picture. He doesn't have a picture, but he explains this picture very beautiful. So maybe he should be cited here.
Oh, okay. Thank you for your note, because the credit can go to him. Anyway, finally, we have motions of the foundation, which is resulted from this filtration effect. And of course, in general, even in the two-dimensional, we have the vertical movements also, but for these vertical propagating shear waves, sway and rocking motions, we resulted, and we name it as the foundation input motion. And when we say foundation input motion, it means that the resulted sway and rocking motion of the relatively rigid foundation. So it is the kinematic interaction and the inertial interaction. When you look at the problem, again, of course, the response of the two systems are different because of the flexibility of the soil. And it can be said that the soil and the structure make a new system with new dynamic characteristics, which means a longer period because of flexibility of the soil here, and usually increased damping, higher damping due to the wave propagation in the soil to the infinity, or it can be reflected in some boundaries, of course. But so the system has a new period. Very simply, when we look at the problem, we have the new different period and different damping, and of course the response would be different. So it's the kinematic interaction effect and inertial interaction effect. Because we use these terms, and I just wanted to mention that for those who are not familiar with the field. After this introduction, okay, so we can classify the soil site effect and soil structure interaction effect, kinematic and inertial effects. And of course, the soil structure interaction affect the elastic and inelastic responses both, and finally, of course, affect the seismic performance of the structure. The regulations of the soil structure interaction, I divided into two sections for this design of new buildings. It was started with, I don't know why it's, okay. Started with ATC 306 in 1978, which was mainly based on the works of the Professor Veletsus from Rice University. And this is the basis of the current provisions near 2003 and also AC7. And the parts of soil structure interaction is almost copy and paste to these documents. Of course, some modifications, but the core of the regulations remains the same from that time. I want to say something here that, of course, soil structure interaction is has a long history. Many researchers have been working in that area. I skipped to save the time to go to the literature review. There are many names. Even want to talk about the major studies, there are tens. So occasionally I may name some of these researchers, like here I made about Professor Veletsus. It doesn't mean that I'm ignoring the others. And also I want, of course, here I refer to our own works in Sharif University, because it's the purpose of this seminar. I'm going to introduce what we did in Sharif University. So it by no means it means that we had very innovative work in that area. And okay, and I think there's something wrong here. Anyway, for the seismic rehabilitation of the existing buildings, we have FEMA 440, which is an improvement to nonlinear seismic static seismic analysis of FEMA 356 and also ATC 40. But they added some parts for the soil structure interaction. Of course, when you go to the rehabilitation of the existing buildings, you have to go to more details, use the capacity of the structures, and estimate what's the response and capacity as precise as possible. And so they added the soil structure interaction And finally, later it became the basis of the ASCE 41 as a standard in this field. We are going to talk about some details of these regulations. That's because after talking about the effect of soil structure interaction using our simplified models, I'm going to compare the results with the current provisions. So based on the NEHRP 2003 and the other AC7, soil structure interaction is a beneficial effect. And because of that, it's an optional. You can use that to reduce the base shear and design for a lower base shear. So the base shear for the soil structure system would be a bit less than, and this difference is a function of the change in the period and the change in the damping of the system that I talked about. And the provisions provide some simplified formulation, which is in the concept of springs in series, to find the period of the new system, and also such kind of graphs that having the change in the period and having the aspect ratio of the structure. H is the height of the structure, the effective height of the structure, and R is the radius of the foundation, or it's better to say the radius of the equivalent circular foundation. So you can find the damping. This damping is the soil-induced dampings. It should be added to structural damping, and from that you can find the difference in the base shear. There is no kinematic interaction effect addressed in these regulations, and this is based on the first mode of vibration. It means that it's considered that the main effects on the first mode and the effect on the higher modes is neglected. And the most importantly, it's based on the elastic behavior of structures. When you estimate the response of the system with its period and damping only, it means that you are estimating the elastic response of the structure. That's why we know that the structures go to inelastic behavior serially during the real strong motions. I don't want to explain about this, just say that it uses the same design spectrum, and you can change, because here I just said that it's a function of these two parameters. Here are more details that you do the change of in the periods. You can find the CS from this formula and adjust it for the damping that you had already. But the thing that I want to talk about, emphasize here, it's just that the changes are out in the denominator of this equation. It means that they are using the same modification factor R for both the soil structure system and the fixed base structures. So extending the findings of the elastic response to the inelastic directly. For the FEMA 440, it considers we can come here exactly, is a free field motion, considering for the kinematic interaction effect as a high pass filter, and also adjusting for the foundation damping. It's because in FEMA 356 they didn't have the adjustment for the damping also, and here also introduced the kinematic interaction effect. So the demand of the structure can be adjusted for both damping and kinematic interaction. But for the kinematic interaction, they just consider the effect of base slab averaging, and also for the effect of embedment ratios for different. They are all reduction factors, and the idea is that kinematic interaction always reduce the input motion than the demands of the soil structure system. We will talk about a bit later. And this is the graphs that they propose for the damping changes, for the surface foundation and for the embedded foundation. I will talk about them at the end of the session. Okay, we go to the simplified solid structure model. This is the simplest model that you can imagine, that using a single degree of freedom model for the superstructure, a rigid foundation. Of course, we know that the foundation is not rigid, but considering the flexibility, make it the problem very complicated. And in the simplified methods, it's a customary that consider that foundation is rigid. And of course, this is the concept behind the current regulations use almost the same method. And this is the soil impedances, I mean, in different degrees of freedom, which of course we know that is frequency dependent. For the soil, for the elastic section, considering the elastic response of structures, you have to see what happens to the period and damping only. Okay. For that, of course, there are many ways of going to the transfer functions, eigenvalue analysis to find the period and damping of the system. I just show a very simple case of the eigenvalue analysis. Is the system, the static stiffnesses and the dynamic coefficients, the stiffness coefficients, we are responsible for the frequency dependency, and you can simply write the mass and stiffness matrices, and you can use the introduce some non-dimensional parameters for the problem, and finally first frequency of the problem. It's one of our works that I did with Professor Fukua. It can be shown that all the problem, the eigenfrequencies of the system, that the period and damping will come from that, can be defined based on some non-dimensional parameters. I use in two groups. One is the non-dimensional frequency, which is somehow the representative parameter of the stiffness ratio of the structure and the soil. The structure and soil. Vs is the shear wave velocity in the soil. And also the aspect ratio of the building, as we saw this, it was appeared in the graphs also. And some other parameters, the relative mass of mass index, mass of structure to mass of the soil, foundation to structure mass ratio, position ratio of the soil, damping ratios, and some other minor parameters we consider, not we consider, it means that it's known that group 1 is the key parameters, and the other parameters can be set to some parameters which covers the ordinary and traditional buildings. This is the results of the change of the period with this A0. A0, as I said, is the index for the relative stiffness of the soil and the structure. When A00 means a fixed base structure, rigid base. When it goes up, it means more severe soil structure interaction effect. And a value of 2.5 or 3, or something between 2 or 3, you can consider as cases with severe soil structure interaction. Graphs for different structures with different aspect ratios, as it can be seen. Slender structures are the period of the slender structures are more affected by soil structure interaction. But for the case of damping, that are slender, the squatty buildings, short buildings, that more affected by the soil structure interaction and may have a large damping ratio. The responses, the results are fairly compatible with the results of the ATC, and it confirms that the results of ATC, of course, derived for the elastic response of structures. Okay, so what's the effect on inelastic response of structures? And more specifically, this SI effect on the ductility and strength demand of structures. Consider this graph as the force and displacement And of course, the slope here is the stiffness of the structure. This is the elastic stress demand. It means that the force in the structure, in the columns, in the spring, if it had a very high strength and never entered the nonlinear range. But of course, we know that we have limited strength, and in some points it starts to go into the plastic range. And of course, the higher displacement, the ratio, of course, between this maximum displacement to the yield displacement, we refer to ductility, and the ratio between this elastic strength demand to the Fy, which is the yield strength, usually called R mu, is the strength reduction factor or yield reduction factor. And we are going to see the effect of soil structure interaction on mu and R mu both. And of course, when we say U, we mean the displacement in the structure itself, because we are ground free, the displacement of foundation, displacement due to rotation of the structure, but we are going to monitor the displacement inside the structure, of course. And after that, we are going to answer the question that the expected ductility demand for buildings designed based on conventional fixed base assumption. It means that usually we design structures and find a base shear based according to codes. But in reality, it's located in the half space in the soil. So we expect, usually we use dynamic analysis, if we do, for example, going to the inelastic dynamic analysis, we expect the results from this model. Okay? But in reality, this is the case. So we have to see that what is the response of this system. And the response of those buildings designed based on the regulations like NERHEP 2003, because we reduce the base shear and design the buildings for a reduced base shear. So we want to look to see what's the ductility demands, the strength demands for these three cases. For the model, here we used discrete models for the based on the works of Professor Wolf. Of course, when we want to work in the inelastic range, we cannot work in the frequency domain. So these kind of discrete models allows you to work in the time domain, but considers for the frequency dependency. And that's the reason that we use that model. This is for the surface foundation, and this is for the embedded foundations. This is not the structure, it's the mass of the foundation, and the eccentricity here provides the coupling between the sway and rocking stiffnesses, okay? And we can construct the superstructure here and analyze it. The superstructure is considered to have a bilinear behavior, and also for the nonlinear behavior of the soil, we use an equivalent linear model with a reduced shear modulus of the soil and the damping ratio based on the level of strain in the soil, or can be translated to the level of shaking. There are some examples. Here the first examples are for 24 records on the alluvium site. I used the records that Miranda used to drive the strength relative factors for the fixed base structures to be comparable with his famous equations, which is used in many places. So these graphs, for the first row is the FE, elastic strength demand. But for these two cases, we have inelastic strength demands for two levels of ductilities. And each figure, this is for H over R1 and T3. And in each figure, we have three lines. The green one is the fixed base, yellow for A01, and red one for A03. It means the case with severe soil structure interaction effect. As it can be seen, the difference for the elastic response is a large difference, which is resulted from the change in the frequency and damping in the system. But when you enter to an inelastic range, the difference becomes much less. It means that although the elastic demand of the structures for the two systems are different, for inelastic case, they become very close. And it means that, for example here, when we look at this graph, the ratio of the two terms are not the same. And this is what is the implicitly behind the regulations in ATC 306 NEHRB 2003 that reduce the, it means that we are reducing the demands much less than really it needs to maintain this level of ductility. So using this radius base shear, one can expect much higher ductility demands in the soil, in the structure as a part of the soil structure system. And this is the results for R mu. Again, the green part is for the fixed space, and as you can see, the R mu, the reduction factor, that it's much less for soil structure systems. We can repeat the analysis for ground motions on the rock and the soft soils, and this is the results for the rock. Again, the same results, and for the soft soils, again the same. I didn't show the fixed space because drawing the central structure factor for the fixed space have to be normalized, and anyway, I skipped that to save time. Anyway, you can see a lot of a large effect of the soil structure interactions on the string structure factors, and this is string structure factors for the soil structure system that we developed in our studies, and the results have been published in 2007 in Soil Dynamics and Earthquake Engineering. So now we start to compare the results, the ductility demands for these systems. For this study, we considered that we have the system has been defined for a fixed ductility for system A, and then we will see what will happen for the systems B and system C. There are two example cases for two specific earthquakes, ground motions. The El Centro, famous El Centro earthquake. As you can see again, this green one is the system C, and the red one, system A, which is a fixed space. And when we design for the, this is for ductility 6, so it means that the red line is straight 6. But you can see that for a system with A02, one can expect very large level of ductility in the systems which has been designed based on the reduce-based shear. Okay, and this is for SCT, the Mexico City earthquake, and of course the results in the nonlinear response of structures strongly depend on the predominant period of the record. And for this record, which is a very long period record in soft soils, this phenomena has started in the long periods here, and you can expect very, very large. Of course, it is meaningless, but it means that the structure is not safe using that. And this is the average for 24 ground motions recorded on the alluvium side. And again, it can be seen that there's a large difference between two results. Okay, I go to the hysteretic energy demand. Of course, when you change the system, it means that introduce the soil beneath the structure, the hysteretic behavior of the structure changes. And it can be more dissipated in energy or less. And I just grab an example here for two cases with A01 and A02, different loops and different, of course, absorbed energy. And using a damage index, for example, here we use Park and Ang damage index. This is a combination of the ductility term and energy term. You can see what's the effect on the damage index. And I just gave one example here. Here we have Park and Ang damage index. Here we have the period of the fixed space structures, again for 3 cases compared to the fixed space structure. And it can be seen that especially for slender structures, one may expect very larger damage indexes for the soil structure systems compared to the fixed base structures. But maybe this graph seems to be very, I'll say, scary. But this resource is not have any practical importance, maybe because structures with such slender ratios usually don't have such kind of periods, of course. But of course, with these aspect ratios, you can find periods in this range, and it happens that sometimes the structure locating in the soil has more damage, and because we usually believe that the soil helps the structure and improves the behavior of the structure, but so it can happen in many cases that increases the damage. Okay, and again, the more results can be found in this paper in the engineering structures. I go very briefly for the foundation. Actually, I was thinking to talk about the foundation embedment, because the embedment is a long story, of course. It's very complicated. When you go to the embedded foundations, you have to take care about the nonlinearity in the soil, the local nonlinearity, the separation of the foundation of and the soil, of course. But here, just as a measure, qualitative, studying the problem, we use this is the problem that we are dealing with. And again, this is the same model that I showed before, using the discrete models of the wolf. And the point is here that for the case of embedded foundations, you have to consider the kinematic interaction also. Even for the simple case of vertically propagating shear waves, as I talked in the beginning of talk here in the first slides, your kinematic interaction effect, and you have rocking input motion. So you have to consider for that. Here we used the same model of Wolf and Meek to compute this foundation input motion elements. And this is the result, some examples. Again, here we have ductility demands for different aspect ratios in different columns. And 3 cases, I'm sorry, I didn't have the color graphs for figures available. For the fixed space A01 and A02. And it can be seen that for the case of slender structures, the ductility demand for deeply embedded foundations can be higher than the ductility demand for the fixed base structure, which has been set to 6 here. Of course, E over R equals 2 is a large value, of course. But we want to talk about the extremes and the phenomena that for the case of embedded foundations, the rocking input motion can play an important role. Of course, it has been known for many years. But I'm talking about that because in the current provisions, we don't look at the rocking input motion, but we look on the reducing effect of kinematic interaction by filtering, by slab averaging. And the results can be different from the real cases. And this okay. Here, different embedded ratios are compared together. As the embedded ratio, it means the embedment increases, the ductility demand in the structure going up. And here I looked at the problem, considering the kinematic interaction and ignoring the kinematic interaction effect. It means when I say without Ki, it means that the input to the system is the free field motion, not the sway and rocking resulted foundation input motion. And comparing the results, for the E over R 0.5, you can see that kinematic interaction reduces the response. By response, I mean the ductility demand of the structures. And this is true even for the case of E over R equals 1, at least for squatty buildings. But when it goes to slender structures, it starts to lead to higher ductility demand. And especially here for really deeply embedded foundations, one can expect higher ductility demands for the system subjected to the foundation input motion compared to the same system subjected to the free field motion. Okay, sure.
The free field is just horizontal, or it's also point rotation?
The input motion, you mean?
Yes.
Yeah. When I say without AI, it means just horizontal.
Or driving motion.
Yeah, and free field motion. But when we talk about the without kinematic interaction effect, it means just horizontal and free field motion. But when we say with Ki, it means both. The resulted sway, it means the reduced one, filtered anywhere, and also the resulted rocking motion.
From inertia
No, 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 no. Not from inertial, from the kinematic interaction. Of course, both systems, of course, are free to rotate. So both of the systems, even without kinematic interaction, has rocking motion in response, which is resulted from the flexibility of the soil. But as the input to the system, we can input just the free field motion horizontal, and of course it will rotate and rock. But we can solve the problem subjected to the resulted sway and rocking, which is resulting from the kinematic interaction effect.
But for vertical
Yeah.
Okay.
Yeah. Oh, sorry, I didn't get. Yes. Sorry. Of course, in the case of surface foundation, you don't have the rocking input motion, but in this case, because it's embedded foundation, even for the vertical, they're rocking. Which part? Yeah. Oh, yeah. Okay. Okay.
Surface foundation, you don't have rocking.
No, of course, we have. We don't, for the surface foundations subjected to the vertically shear waves, there is no rocking input motion due to kinematic interaction. Yeah, it's a very simple case. So the next topic that I want to talk about in the next 5-6 minutes is the equivalent linearization. The reason, again, is the FEMA 440 used this equivalent linearization to approximate the performance of the soil structure systems. The concept of equivalent linearization has been around for many years. It means that I'm just talking about the fixed base structures. For a system with period T, damping psi, when a ductility demand, not capacity, ductility demand mu, we can find an equivalent system with equivalent period and equivalent damping to have the same response. Okay? Of course, it's not a unique answer, but you can find it. And the first attempts was using a second stiffness, considering behavior, and it's a maximum ductility in the system, maximum displacement in the system. And then associate the damping ratio with these, the period resulted from this second stiffness to find the response of a structure. So from the second stiffness, you can find T equivalent, and after that, play with the damping to have the same response as here. And this graph is from FEMA 440. It employs this concept. For example, here for the second stiffness, this is in the capacity spectrum method. We can ignore this part, for example. And after that, they come with another idea, but instead of using the second stiffness, it's better to use an effective stiffness, which is something between the initial stiffness and second stiffness. and combine this effective period with an effective damping ratio to get the response. For that, and FEMA 440 used this concept and combine it with a well-established, almost considering all assumptions of the this changing a soil structure system to an equivalent structure, fixed basis structure with equivalent period, equivalent damping, and equivalent ductility. It means that this ductility is in the structural ductility as a part of the soil structure system, but here it has just 1 degree of freedom and 1 ductility, so it's the system ductility, and they can be derived in the closed form to find that. And we know this problem, and suppose that we have solved this problem for the fixed basis structures. FEMA mixed both of them, so starts from here, making a fixed basis structure with equivalent parameters, and after that change it to the equivalent linear system with equivalent, and get rid of this ductility. But it's a separate analysis. It's a separate analysis. The results of here, which is mainly based on the works of Professor Ivan from Caltech, has its own assumptions. It doesn't mean that you combine both of them together, at least theoretically. So here we want to look at the problem that if we start from this one and directly go to this one, it seems that it means that exactly the work that Professor Ivan did started from this, go to this. We can start from the soil structure system and find it, and to see that what's the difference between the results. Okay. So first, I need to talk about the concept of equivalent linearization that Professor Ivan used. It's a error index, which is the difference between the responses of this original system and this equivalent system divided by the right answer. So in a plane, equivalent period and equivalent damping. In this plane, we can search point by point to find it. That's the error. Of course, there's no unique answer, and you can find a line here which is 0 answer. It means that any point on this line gives you the right answer. Okay? But it's valid only for one ground motion. If you can repeat it for different ground motions, it means that the line, of course, are not the same direction. So there are the dispersion. So you have to look at the problem probabilistically, not this way. So this is the results from Ghannad and Ivan. This is the mean of errors and the standard deviation of errors. And of course, this line, the 0 error, is different combinations have different standard deviations. Okay, so we can start to define and measure for the error, and it's we can define engineering acceptable range, and he defined it as a -10% to +20%, and said that results here, I name it acceptable, and compute the probability of the results being inside that or outside that. And draw to the contours here is the probability of the being inside this one, being outside of this area. And this point, which is the 0 probability, this is the minimum FEAR, which means it's the abstraction for the engineering acceptance range. Okay, so this is the answer here. It's not exact for different ground motions. You can dispersion in the results, but it's the best results from the probabilistic point of view. If you move in this direction, the diameter of these elliptical shapes, it's not so sensitive, but perpendicular to that, it's very sensitive. If you move from this way, the probability start to increase very rapidly. So it's better to be here or to move around this line. Okay, this is the concept that I1 used to come to these optimum points for different systems. Now we're back to our own problem. This is the graphs that we generated for the soil structure system, just one sample. It's very similar. This is for the fixed space, which can be compared with the results of I1. We tried to use the same database as he did. And it goes for different soil structure systems. The shape of the contours is going to be changed. The sensitivity as analysis of the results increases with the soil structure interaction. But as we'll show later, the reliability of the results for the soil structure interaction increases with increasing parameter A0. This is the results for the change in the T equivalent over T for the soil structure systems. Again, for different values of A0 and for different values of H over R, ABC is written here. This is squatty buildings coming to slender structures. As you can see here, even for the value of ductility 1, which means elastic case, we have elongation in the period. Of course, it's due to soil structure interaction. For the elastic case, you have elongation in the period due to soil structure interaction. As you go to the right, it's a combination of the soil structure interaction effect and the flexibility and the equivalent elongation of this nonlinear behavior, this K equivalent. This is almost parallel here for the squatty structures. But when you come to slender structures, because you have a large elongation, even in the elastic case. So when you go to the right, it's almost constant. And one can say that it's a trade-off between base flexibility and the structural dynamics, and is the effect. For example, for the linear systems, the whole responsibility of for the base flexibility, because there is no ductility in the system. As the ductility of the system grows, it means that you enter the more and more in the inelastic range. There is some portion due to base flexibility and some portion due to structural dynamics. But never this will be omitted. It means that even for the highest nonlinear structures, flexibility of soil plays some role. And this is the same results for the damping. Again, as you may remember, we said that for the effect on the damping and the period, elongation of period, slender structures are more affected by the soil structure interaction, as we saw in the previous slide. But for the damping, squatty buildings, short buildings are more affected by the soil structure interaction. So for this structure with H over R 0.5, we have a lot of damping in elastic case. And when you go to the inelastic, it reduces. It means that the damping which was used to come from the radiation damping in the soil doesn't exist anymore. Or better to say that it's less important. So it reduces, and they all converge for the very large ductility demands. And for the very slender structures, soil structure systems, A03 for example, can have lower dampings even compared to the fixed base structures. Of course, the discussion here depends on the damping model. We model damping as a viscous damping, and it happens if you damping model the damping as a hysteretic damping. It doesn't happen, it never comes from the fixed base structure. But anyway, I wanted to emphasize that for this case, it starts with a high value of damping and go down. But in this case, is different.
Question, but the soil is linear all the time.
Yeah, the soil is the soil.
Then if the structure, if motions are so large that the structure goes nonlinear, soil may go nonlinear before the structure.
Yeah, sure, of course.
Just a minute.
So
It may or it will.
Yeah, it will.
depends on the soil, soil.
I don't think
So-
it depends. It
I mean,
always goes nonlinear.
if we ask geotechnicals, I mean, I'm not geotechnical, but I've heard that, soils are granular materials.
Yeah,
They are very, very nonlinear.
Yeah, they asked me to repeat the questions. Yeah.
It looks more solid.
Yeah, the question is that when we have a nonlinearity in the structures, of course, we have nonlinearity in the soil before that. And that's true, and maybe the reason is also I'm not also a geotechnical engineer, I'm a structural engineer. But just kidding. But I'm introducing just the damping in the soil based on the equivalent ratio, equivalent linear model. Okay. So okay.
Wait, you're looking at radiation values.
Yeah.
But we just mentioned that soil gets to be nonlinear. Before the soil gets nonlinear, you have a lot of scattering values. You don't consider that.
Yes.
And when the soil gets nonlinear, there is incredible amount of energy wasted there. You don't consider that either.
Yes. You're right, completely. Right. Yes. As I said, it's a. You are completely right. The main, very important factors, but I'm using a simple model. It doesn't mean that so you are using a simple model, so it means that the result can be meaningless. Maybe somebody say, but the model is very similar to the simplified models which is used in the practice. And I'm not going to say that the results here is the exact results that can be used in practice or in the codes, for example, going to that. I'm going to say that there is such kind of phenomena because for example, the FEMA uses this problem and this problem, mix them and come to the solution. Okay, this problem exists even there. Of course, in the codes there are simplifications, and nobody expects that code be perfect. But we want just to mention that if we want to go to this one, we can look at the problem in a better way, at least one step, just. And I think after that, I just one slide left, and this is the ratio of the equivalent period of the FEMA to the equivalent period that we derived here, and the ratio of the dampings here. Of course, this is for the FEMA, and you can say that in some parts it's lower and larger and lower, and nobody can say that which one is better because there's no unique answer. You can move it here. You can say that if you have longer periods and larger damping ratios, maybe you have good estimation of the results. Okay, so it's better to look at FEEAR. It means the probability of the falling down outside the acceptable part. And if you don't remember what's the definition, it was the definition. And looking at that is the gray one is the FEMA 440 and the blue one is the results of here. And you can see that for the A01 are very similar. It means that you can combine two separated problems to come to the result for your own problem here. But as you go for larger values like A0, there is a difference between two results. And it means that the results of the FEMA 440 is less reliable, of course. And even we ignore this case as an extreme case for the A0 equals 2, we can start here. And the main reason here lies in that this graph, that FEMA 440 gives this graph to estimate the foundation damping, which can be compared with those in the ATC or NIHR. And you can see, for example, for one case, 1.6 as an example here. Here it leads to about 11% of damping. It's more than 20% damping here. And it means that the damping ratio presented in FEMA 440 is less than those already existed in for the elastic cases. And probably, I think, they reduced the damping to get a better results for higher damping ratios, and they were successful in that because we have very good results for the higher ductility. But for the near elastic cases, the results are overestimated almost. Okay. So, just the conclusions. I don't know, go to the conclusions or not because time is. Go. Okay. So, I just read it. It's emphasized that soil strongly affects both elastic and inelastic structure response to earthquakes through soil-structure interaction, and any rational study and performance evaluation of buildings should be considered for this effect properly, of course, as known. SSI affects elastic and inelastic response of structures in different ways. It means that stress reduction factors would be different for soil structure systems and fixed basis structures. Soil structure interaction generally reduce strength and ductility demands of structures, except for the rare case of short period slender structures and slender structures with deeply embedded foundations. And buildings designed for a reduced base shear as permitted by current seismic provisions to use the beneficial effect of soil structure interaction may experience higher ductility in comparison to buildings designed based on conventional fixed base design concept. And based on the results presented here and other valuable researchers done by other researchers, it's believed that nonlinear response of soil structure interactions, soil structure system deserves much more attention, and there is a need for appropriate simplified methods to address this issue. And of course, many other issues such as detailed study on kinematic interaction, deep foundation, explicit nonlinearity in the soil structure interaction, and multi-degree of freedom systems and higher modes foundation uplift, which deserve special attention, were not addressed here. And finally, I want to thank the individuals, the graduate students in Sharif University, which are all of them are PhD students in different universities in Iran, in the world. The results which I presented here was the results of hard working of these students, and also some other students, and many of them are here, PhD students in University of Southern California, which worked in the soil structure interaction in our team during the last years, but I didn't talk about the results of them here today. Thank you.
So if we have people on the internet willing to ask questions, make sure you raise your hand. You have a little box to raise your hands, and we'll be able to accommodate your questions. And now we're going to take questions from the audience. So any question for our speaker?
I have some comments. I don't have
Okay, Misha. All right. Please.
Okay. One comment I have is that many conclusions you have are a consequence of rigid foundation. And of course, you know that this doesn't really hold. So I suspect that some of the conclusions that you made about the differences between tall, slender structures versus low, squat structures will not hold. Because with the wave passage effect and rocking excitation, the vertical pseudostatic rotation will almost double, maybe even triple the drifts, so that the differences will be much less, and maybe the squat structures will be just as well affected. Okay. But the other comment is a little bit aggressive. And it's not personal. It's not personal, okay? I review papers and I review proposals, and I'm fascinated how many very capable professors spend a lot of time doing things within the framework of FEMA. And it seems to me you're doing the same thing. You enter this space of constraints. FEMA did this, FEMA did that, FEMA did that, and then you start manipulating in there. Why don't you start writing papers about what is wrong with FEMA approach? I mean, this is so restricted and so naive and so limited. I mean, and you don't have infinite amount of time. How about writing some comments and papers on soil structure interaction? I mean, Andy Villetos was an incredibly good guy, but the stuff that they used from him is like 50 years old. Well, maybe 40. So anyway, this is my comment. You can comment on my comment if you like. You don't have to.
We give you a chance to answer to that.
No. Of course, as I said, it's a great honor to have your comments, of course, really. Of course, I start with the second comment, the FEMA 440. Yes, for example, in the case of the last thing that I was talking about, the equivalent linearization, we tried to do the same thing as you said. I believe that we tried to make our own solution, starting for the soil structure system, going to the equivalent fixed base structures. Of course, in the framework of the assumptions that they made in that regulations. But we generated our own results and compared those results with the results in the FEMA 440, for example. And we believe that it's more reliable because it's more rational. But of course, there are many shortcomings in this approach and these results because of the assumptions that we made, which is partly your first comment, which is not realistic. But it's in the framework of the assumptions that they made to produce the regulations. I have done some works in the flexible foundations a bit. Actually, here one of the students here is Rahimian. He worked on the flexible foundations, and of course, when you work in the flexible foundations, you have to look at the structural system. For example, if you have a wall where it's located, center of this foundation, and a lot of variation, of course. And you can start to understand what is going there, but it's hard, at least for me, to summarize them in a way that help the others to think about that and to make a decision and parametrically. And of course, I know it's, at least for me, it's a long way to go. Although I don't have a lot of time, but I agree with your comments, and really I appreciate that. And I said it's a great honor for me to hear your comments.
I have a question about Eurocode 8 and possibly the Japanese code. I'm just curious if you know about how these two particular codes account for soil structure interaction.
Actually, I'm not well familiar with Eurocode 8. As far as I know, there are some sentence, some paragraph there that soil structure interaction is a phenomena that should be considered in a proper way. At least up to a few years ago, I know that this was the only regulations in the Eurocode, as far as I know. I don't know if you can make comments if you any speak.
Europe, you know, there are no earthquakes in Europe.
Oh, okay, maybe, yeah.
And the code is written by
Yeah.
Germans and French.
Oh, okay, maybe
so
that's the reason.
Comments and say, well, see, we told you.
Yeah.
That's the end of it.
So that's there's no.
Yeah.
But in Japanese, as far as I know, Japanese didn't have any regulation on soil structure interaction. I mean, in the standards. Of course, a lot of knowledge, but in the standards before 2001, I think. After they started to introduce into the code, but mostly, as far as I know, it's based on the experimental studies, not analytical studies. And again, as far as I know, they don't look at the nonlinearity in a structure directly. But if you are working with experimental data, it means that everything is included there. So maybe this is the vision there. This is what I know.
Can I make one more question? Not a comment.
But you have to be recorded, so you're nicer.
All right. It's a very nice question. No controversies about it. you have established a procedure and certain steps and assumptions, and then you kind of calibrate this and compare this with what is in the ATC and so forth, in NIHRP and so on. Why not take, say, 2 or 3 buildings for which we have very detailed data? And like, we can give you data here in California. We don't have many, but like 4 or 5 buildings. And then you can go through these buildings and verify to what extent the modeling assumptions that you made will go through against the data, rather than go to code. You see, that will be much more realistic test of some of the assumptions.
That would be the final question.
Okay. Yeah, of course, learning from the nature, it's not nature, the building instrumented buildings, this is the correct answer. And you can use that to calibrate your models, find the phenomena. But I never used that. I was not in that field. Actually, I did some experimental works during my PhD, but it was not the main part, and it was mainly on the elastic part. And you know better than me that there are many dispersion there, and you have to be. I think if you go to that field, it means that you have loved that field to spend a lot of time on that. So I started with working with the analytical studies, and I agree that it's not a good idea only, it's essential to do that. But I have never had the chance to do that. I leave that to Professor Todorovska and the others to do that for us. Thank you very much.
Thank you very much. So this will conclude the seminar. And again, I think we should, before we exit the room, congratulate our speaker. Thank you.